We begin our journey far from the sunlit surface. Here, a specially designed submersible is our only vessel. Slowly we sink. The blue light of the upper waters fades above us, first to a dim twilight, then to an inky blackness. We are entering a realm few have ever witnessed. The pressure mounts with every meter we descend. It is a silent, crushing force, a constant reminder of the alien world we are penetrating. The ocean's true depths await our arrival, holding secrets for millennia. Down, further down, we continue our descent. The last vestiges of sunlight vanished long ago. We are now in the midnight zone, a world of perpetual night. Strange bioluminescent creatures may flicker past our viewports. They are like fleeting ghosts in this eternal darkness. The temperature plummets, the water becoming icy cold. This journey is not for the faint of heart. It is a voyage into an environment more hostile than space, yet teeming with mysteries we are compelled to explore. Finally, after hours of descent, our sonar indicates we are approaching the seabed. The abyssal plain stretches out unseen around us. Our powerful lights pierce the darkness, but they illuminate only a small patch of this immense hidden landscape. We are hunting for something truly extraordinary, the lost city. Our submersible glides slowly over the dark, silty bottom of the Atlantic. The terrain is monotonous for a time. Then our sonar detects something unusual ahead, a large structure rising from the seafloor. It is not a natural volcanic seamount of jagged rock. The shapes are different, more delicate, almost organic in their form. Excitement builds within our confined space. Could this be what we have traveled so far and so deep to find? The pilots guide our craft closer, our lights straining to reveal the truth hidden in the gloom. And then we see it. A pale, ghostly form emerges from the darkness. It is a tower, but unlike any tower built by human hands. It shimmers in our lights, a stark white against the black backdrop of the deep sea. This is not the product of violent volcanic eruptions, like the black smokers found elsewhere. This is something different, something unique. We have arrived at the edge of the Lost City hydrothermal field, a place of incredible, unexpected beauty hidden from human eyes for eons. Spires and columns of pale carbonate rock rise majestically from the seafloor. Some reach astonishing heights, towering up to 60 meters like ancient, silent sentinels. The sense of discovery is palpable. We are explorers in an alien landscape on our own planet. These are not the black smokers many are familiar with. Those are found at volcanic spreading centers. They are intensely hot and spew out dark, sulfide-rich fluids. The Lost City is different. Its spires are made of carbonate minerals, like limestone or marble. They rise from the mantle rock of the Atlantis Massif, a mountain pushed up from the Earth's interior. The towers themselves are a marvel of natural architecture. They are porous structures, riddled with tiny channels and vents. Warm alkaline water, rich in dissolved minerals, percolates upwards through them. As this water, heated by reactions within the seafloor rock, meets the cold ambient seawater, minerals precipitate out. This is how the chimneys grow, layer by layer, over vast timescales. Some are slender and delicate. Others are massive, broad structures, testament to millennia of slow, patient construction by the Earth's deep chemistry. The tallest spire, named Poseidon, stands as a monument. It is a staggering 60 meters high, taller than many buildings on land. The beauty of these ivory towers is almost haunting. The chemistry at Lost City is unlike that of any other known hydrothermal vent system. It's not driven directly by volcanic heat from magma. Instead, a process called serpentinization is the engine. Seawater percolates deep into the cracks and fissures of the mantle rock, exposed on the seafloor. This rock, peridotite, is rich in a mineral called olivine. When olivine reacts with seawater at moderate temperatures, around 90 degrees Celsius, it transforms. It produces minerals like serpentine, and crucially, it releases hydrogen gas and methane. This production of hydrogen and methane is incredibly significant. These are energy-rich molecules. On the dark seafloor, far from the sun's energy, they can serve as the basis for life. The fluids venting from Lost City are also highly alkaline, with a pH similar to household ammonia. The temperatures are also milder, typically ranging from 40 to 90 degrees Celsius. These conditions are less extreme, perhaps more conducive to the delicate chemistry that might lead to life's origins. The serpentinization process provides a constant supply of the raw materials and energy needed for a chemosynthetic ecosystem. The conditions at the Lost City hydrothermal field offer a tantalizing glimpse into our planet's distant past. Imagine Earth, about 4 billion years ago. It was a very different world indeed. The atmosphere was thick with gases like methane and ammonia, but there was little to no free oxygen. Volcanic activity was rampant everywhere you looked. The young oceans were likely a chemical broth, rich in dissolved minerals from the cooling crust. It was in such a primordial soup, scientists believe, that the first sparks of life ignited. The Lost City vents share remarkable similarities with what we theorize about early Earth environments. The serpentinization process, producing hydrogen and methane, could have been widespread on the early seafloor. These gases would have provided a ready source of energy for the very first forms of life. The alkaline conditions found at Lost City are also thought by some scientists to be more favorable for the formation of complex organic molecules, the building blocks of life, than acidic environments. Deep within the porous walls of these carbonate towers and in the waters they expel, life does indeed thrive. But it is not the life we are familiar with from sunlit realms. There are no plants here, no algae. Instead, we find a unique community of microorganisms. These are bacteria and archaea, ancient forms of life. They are adapted to survive in this extreme environment, drawing their energy not from sunlight, but from the chemical reactions occurring around them. They are the foundation of this hidden ecosystem. These microbes are chemosynthesizers. They utilize the hydrogen and methane gushing from the vents. The hydrogen, in particular, is a powerful energy source. Some microbes combine hydrogen with carbon dioxide dissolved in the seawater to create organic matter. Others metabolize methane. They are the primary producers in this dark world, much like plants are on land. They form dense communities, living within the chimney walls and in biofilms on their surfaces. It is a testament to life's incredible adaptability and tenacity. Exploring the Lost City is an immense technological challenge. It lies at a depth of around 800 meters or half a mile down. The pressure here is crushing, about 80 times greater than at sea level. No human could survive unprotected in such an environment. Therefore, we rely on sophisticated robotic vehicles. Remotely operated vehicles, or ROVs, are our eyes, ears and hands in this alien world. These incredible machines are tethered to a surface ship by a long umbilical cable, providing power and transmitting data. These ROVs are equipped with an array of scientific instruments. High-definition cameras capture stunning images and videos of the vents and their inhabitants. Powerful lights illuminate the perpetual darkness. Robotic arms, controlled with great precision by pilots on the ship above, can collect samples. They can pick up rocks, sediment, and even delicate chimney structures. They can also deploy sensors to measure temperature, pH, and chemical composition of the vent fluids. Each dive is a carefully orchestrated mission, pushing the boundaries of deep-sea exploration. The data and samples collected are invaluable. The discoveries at Lost City have profound implications that reach far beyond our own planet. The unique chemistry driven by serpentinization and the thriving microbial life it supports offer a model. It is a model for how life might arise and persist on other celestial bodies in our solar system. Specifically, scientists are looking towards the icy moons of Jupiter and Saturn. Moons like Europa and Enceladus are now prime targets in the search for extraterrestrial life, thanks in part to what we've learned in our own deep oceans. Europa, a moon of Jupiter, is believed to have a vast saltwater ocean beneath its thick, icy shell. There is evidence that this ocean is in direct contact with a rocky mantle. If this mantle contains olivine-rich rocks, similar to those at the Atlantis Massif, then serpentinization could be occurring there. This process would produce hydrogen and methane, providing potential energy sources for life. Hydrothermal vents, perhaps resembling Lost City, could exist on Europa's dark seafloor, creating habitable oases deep beneath the ice. Similarly, Saturn's small moon, Enceladus, has astonished scientists. The Cassini spacecraft detected plumes of water ice and organic molecules erupting from fissures near its south pole. These plumes are thought to originate from a subsurface ocean. Analysis of the plume material suggests that hydrothermal activity is indeed taking place on Enceladus's seafloor. The Lost City hydrothermal field stands as a profound testament. It speaks to the intricate and often surprising ways our planet operates. It is a reminder that even in the most extreme and inaccessible environments, beauty and complexity can flourish. Its towering white spires, built slowly over millennia, are monuments to the power of geological and chemical processes. They guard secrets about the very origins of life on Earth and perhaps about the potential for life elsewhere in the vast cosmos. This is a place of deep wonder. The ongoing research here continues to challenge our assumptions. It expands our understanding of the conditions under which life can exist. The discovery of ecosystems thriving on chemical energy rather than sunlight has revolutionized biology. It has opened up new avenues for astrobiological research. The thought that similar hydrothermal systems could be active on distant moons, nurturing life in their dark subsurface oceans, is truly captivating. It fuels our innate human curiosity and our desire to explore the unknown. Yet, many mysteries remain. We are still piecing together the precise sequence of events that led to the first living cells. The Lost City does not provide all the answers, but it offers vital clues.